All right. Hello, everyone. So this week we have, we have essentially completed the essentials of the representation theory for finite groups. So as a result, I'm going to do a summary of the fundamental points. So I'm going to start with this group thing. So let G be a finite group, right? So we do this only for finite groups. And then we have said something about representations and the characters of representations and things like that, right? So the relationships, the first relationship is that the number of conjugacy classes within the group, obviously, that's equal to the number of irreducible representations. I mean, number of inequivalent irreducible representations, but I'm not going to say inequivalent in there. So we have to understand it like this. So irreducible representations. Okay. So in the past week, I have actually shown the number of conjugacy classes by C and the number of representations by NC, but I'm going to just use a single notation for that, right? So I'm going to use the letter C to describe this. Okay, so the second relationship is, well, each of these have some dimensions. So the relationship is that the sum of the dimensions of these irreducible representations is equal to the order of the group. Okay, so d mu is the dimension of the mute irreducible representation, mute irrep. Okay. And G is the order of the group. So that's the next thing that we use. And then we have the character relationships. So there are like two kinds. So the first kind says that if I sum over the conjugacy classes of nk is the number of conjugacy class, number of elements within the kth conjugacy class. So that's the character of the mute representation in kth class. It's complex conjugated. And for the other representation, the character for the same class again. So this is sum over classes, so therefore there's a number of elements within the class appears in here. That's equal to delta mu. And we have a related relation. In that case, we actually have the same expression, but the sum is over the irreducible representation index. Okay. So in that case, I'm going to take nk out over G. So that's a sum over mu chi mu complex conjugate K chi mu L. So here the representation indices are the same and it's summed over. And the conjugacy class indices are different, right? I didn't show this, but it basically comes from the unitarity of some matrix that we can define, right? So I have said something like that. So if I define a matrix like this, UK mu, where the coefficient is the square root of nk divided by the order of the group and the character of mute representation. In that case, the first relationship is just the, I think it is u dagger u being equal to identity, and the second relation is u dagger being equal to identity, right? So because of the fact that the number of conjugacy classes is equal to the number of irreducible representations, this implies that that matrix is square, and well, the first relationship is unitarity, so therefore the second relationship is implied, right? something like that. Okay? So, I mean, it's just a reminder that we don't need these unitary matrix, but we will make a table of the characters. So the first relationship is called the orthogonality of the characters. And second relationship is called the completeness of characters, right? So these are the relationships that, the important points that we are going to use. And there's this other relationship, so I'm just going to squeeze it in here. So I'm going to use with a blue color like that. So if A is any representation, A can be decomposed as a direct sum of these irreducible representations where the U1 appears M1 times and U2 appears M mu times and so on. We usually express this as like a summation symbol like that, M mu U mu. Okay. In that case, this implies that the character of A for the kth class, for example, is equal to the sum over mu, M mu, and the character of mu, the kth class, or something like that, all right? But since the characters in here satisfy that orthogonality relationship, I can use this equation to solve this M mu. So from here, we basically get M mu to be equal to 1 over G times sum over K. Let's see, chi MK is in here. Chi mu K complex conjugate and chi AK. Right? And that's the one that we are going to use a lot when we have a representation and we would like to decompose it into this irreducible representations, and we would like to find how many times a given representation appears in the decomposition. Okay, but that's something else, right? So today I'm going to talk about the character tables. So character table, because we need these kind of tables to actually do the decomposition. Okay. So in that case, what we do is this. First of all, we just write down the on this top row in here, we just write down the classes in here. So basically all the conjugacy classes. I'm going to write CC in here. And sometimes we are going to write down the number of elements within this conjugacy class, because this is also an additional important information, right? And on here, we are just going to write down the representations. Okay, so there's also the number of representations, irreducible representations, is equal to the number of classes. We basically have a square thing in here. So in any case, if I have like the mute representation in here and the kth class in here, right? The corresponding entry in here would be the character of that representation for that class, right? So in any case, I mean, this is the table that we would like to construct. But there's something that we actually use all the time. So by convention, the first column belongs to identity elements conjugacy class. Okay, so C1 is the conjugacy class of identity. So there's this just identity in here. So it has only one element, right? In that case, the characters in here are just the dimensions. So we get D mu in here and EC in here. So therefore, the first column is equal to the dimensions of the representation. So as a result, I mean, this is one of the important place to look at, right? You first need to look at these dimensions first. So we also know that the sum of the squares of that column, sum of the squares of the entries of that column gives you the order of the group. So therefore, that's one of the things that you may want to check, for example. Okay, why this is the case? Because the character of for identity is basically the trace of the matrix for identity, but that's basically an identity matrix. It's a d mu by d mu identity matrix, so therefore the trace is equal to the dimension. And second thing is, well, the first row is basically is reserved for the trivial representation. First row belongs to, sorry, belongs to the trivial representation. So that means all of these entries are equal to 1. So that's the one-dimensional representation, that all the entries are equal to 1. Okay, so that's the simplest representation that we know. It's also, in a way, the most symmetric representation, because when you apply the group element, the vector doesn't change, right? So that vector is the most symmetric vector in a way. So as a result, even though it looks like a trivial representation, but it corresponds to the most symmetric one. So therefore, it's one of the most important representations of it. And usually we just choose them in such a way that the dimension increases as you go down the columns. So as a result, the largest representations with the largest dimension appear last. In applications, depending on what the group is, these representations have special names, especially for some certain molecular groups, for example, molecular symmetry groups. They have some special names. These are published, and so as a result, a lot of people are actually using them. So there are like letters like A, B, E, and things like that. So when we actually work with actual representations, we are going to use these notations. But for I don't know, explaining I don't know the basic concepts, I'm just going to use this u mu expression for expressing the irreducible representations. Okay. So in any case, I'm going to start with this group. Okay, so this is S3. So you remember these are the permutations of 3 objects. Like objects. Okay. So this group has 6 elements. And there are 3 conjugacy classes. So I'm just going to write them down. So the identity has the conjugacy. Well, the identity has the conjugacy class of itself. So that means there are like only 1 element in here. The second conjugacy class is the conjugacy class of the transpositions. Okay. So as a result, the transpositions in here, like the exchanging the places of 1 and 2. 1 and 3 and 2 and 3. These are all conjugate to each other. So there are like 3 elements in there. And the last conjugacy class is the 3 cycles. So there are only 2 elements in here. 1, 3, 2. So there are, in the third conjugacy class, there are 2 elements. Okay. So that means there are C equals 3 irreducible representations. And so I'm going to choose the dimensions in the same way. So in any case, the relationship that they satisfy is that sum of their squares should be equal to 6 because of the first or the second relationship that I have written down at the beginning of this lecture. Okay. Sum of the squares of the irreducible representations is equal to the order of the group, and here it's a equal to 6. And let's just remember that the dimensions is a positive integer, and so therefore there's only one solution in here. If the first two dimensions is equal to 1 and the third one is equal to 2. Okay, so as a result, in that group, we can easily find the dimensions because I know the structure of the group. I know how many conjugacy classes are there. And by using that relationship, we can determine that, right? So as a result, there's no other solution. So I'm going to write down the character table in a moment. But let's say that this group is also isomorphic to what we call as the dihedral 3 group, right? So D3 is the symmetry group of a triangle. Okay. In 2 dimensions, right? So this D3 is actually a subgroup of the basically the rotation group in 2 dimensions. It contains rotations as well as reflections. So I'm just going to show it like that. I think I'm going to use a green color like this. So first of all, there's this identity element, and there are these reflections. So I'm going to show them like that. So these are the mirror planes of the reflection. So that's sigma 1, sigma 2, and this is sigma 3, right? Yeah, whatever. Sigma 3. So there are these reflections, and then I'm going to use this color. There are also these rotations. So if I rotate this by 120 degrees along this direction, or 120 degrees along that direction, these are also symmetries. There's also identity in here. So in that case too, I can clearly identify 3 conjugacy classes. Right, so the first conjugacy class is the conjugacy class of identity, obviously. So in that case, the identity is the identity matrix, right? So it's a 2x2 matrix, basically. Let's just remember that this is a subgroup of the orthogonal group. So as a result, the identity is actually a 2x2 identity matrix. In any case, the second conjugacy class is the conjugacy class of the reflection. So this actually contains the reflections, sigma 1, sigma 2, and sigma 3. And the third conjugacy class is basically the rotations. Let me say it like that. So that basically contains a rotation by 120 degrees and a rotation by minus 120 degrees. Okay. I can also think of this group as a proper rotation group or a permutation group like that. But the conclusions are essentially the same, right? I mean, the groups are isomorphic. These 2 groups are isomorphic, so they have the same structure, same conjugacy classes, but the elements have a different meaning. Okay, so that's the only difference. But they are going to have the same character table, basically, because the character table does not depend on the meaning of the group elements. It depends on the structure of the group. And since the structure of the group is the same, we get the same. So let me quickly write down the number of elements within each conjugacy class also in here. These are basically identical to that case. Okay. So in any case, for constructing the character table, that's what I'm going to do. So the group is S3. I'm going to write the conjugacy class in here, classes. But let's just remember what these things are. So these are transpositions and these are 3 cycles. Number of elements is 1 in here, 3 in here, and sorry, this is M2, and this is equal to 2. And here I'm going to write U1, U2, U3. As I said, I mean, the actual letters used are actually different than this. So in the first column, I'm going to write down the dimensions. In the second column, in the first row, I'm going to write down the trivial trivial representation. So as a result, there are like these 4 elements that I don't know yet, and I would like to find. And for this reason, I would like to, I mean, there are some certain ways that we can actually find them, but I'm going to actually list some properties that we can actually use to identify these, right? So 2 of these properties are the orthogonality and completeness relationships. Orthogonality relationship is basically the orthogonality of a row to a different row. For example, these 2 rows are orthogonal to each other. When we write down this equation, we get a relationship that involves x and y. So since this is a relation that involves 2 unknowns, probably that's not enough for us. So as a result, I'm going to say something more about that. Okay. Or the orthogonality of the columns, which is basically the completeness relationship. So we can talk about the orthogonality of the first column to the second column, for example. There are some certain relations like this. But I'm going to look at this second row in here. So that belongs to a one-dimensional representation. Okay, so let's just say it like this. Right? If A is one-dimensional representation. Okay, so the dimension is equal to 1. Then, well, each A of G is a number. Each A of G is a number, obviously. It's a 1-by-1 matrix, but I have said that it's like I'm not distinguishing 1-by-1 matrices with the numbers. I can think of them just simply as numbers. I need to say one important thing here. If AG is a one-dimensional representation, then AG is a complex number with modulus 1. Just a moment. Is a number with modulus 1. Why this is the case? Because if the group is finite, there's actually a number. I don't know, let's say that m, this mth power of the group element is equal to identity. But this is also satisfied for the for A. So A of identity should be equal to 1, so that's the identity matrix. But the 1-by-1 identity matrix is equal to the number 1. So this side is equal to the nth power of this actually. So this actually implies that, right? So sorry about that. So if G has, that element has order m, then AG is an nth root of unity. Okay, which means A of G can be equal to the exponential of 2 pi I over m times k, where k is one of these numbers, right? It is 0, 1, or up until m minus 1. Okay. So on the complex plane, it's actually a number on the unit circle. I think I'm going to show it like that. So 1 is one of them, but you can actually find the other ones like that, right? So each of these numbers actually they differ by an angle which is like 2 pi over m or something like that. Okay. So it can be a real number, it can be 1 or minus 1 too. That's a possibility, but I mean in general that's a complex number with modulus 1. But not only that, if you also know the order of the element, then you also know that what kind of a number can it be. Okay. So in this case, for example, I mean, let's just remember this. In this case, for example, this second class contains the transpositions, right? And so therefore, they have order 2, and so therefore x must be a square root of unity. Okay, so let's say it like this: for u2. Okay, let's say it like that. So if g is in the second class, so that means g squared is equal to identity, which means u2g squared is equal to 1. So that means x squared is equal to 1. And for the third class, so these are 3 cycles. I don't know, for example, this is like 1, 2, 3, or 1, 3, 2. So the order of these elements is equal to 3. So the third power is like that, whatever. So y cubed is equal to 1. Okay. So this tells me that the x, for example, can be either +1 or -1, and y can be 1 or e to the 2 pi I over 3, or e to the -2 pi I over 3. Okay. So that number is equal to, if you remember, it's -1/2 I square root of 3, and that number is equal to -1/2 minus I square root of 3. Sorry, that's square root of 2. Square root of 3 divided by 2, right? So on the unit circle, these are numbers which are basically equally spaced in terms of angle. So that angle is 120 degrees. So yeah, whatever. Okay, so x can be one of these and y can be one of these. So in this table in here. Okay, so that's the first thing. So there are like 6 options in here. So we have to actually select some and then use this. So the next thing that I'm going to use is basically there's actually a group multiplication table, and sometimes we can actually see some of these. So for example, for that group, product of 2 transpositions gives us a 3 cycle. Okay, so product of 2 elements within that class gives us something in here. So, I mean, I'm just going to start with this. For example, the product of 1, 2, and 1, 3. For example, let's just do this product. So this 1 maps into 3, and then 3 is left invariant. So 1 maps into 3. So how about 3? 3 is mapped into 1, and 1 is mapped into 2. So 3 is mapped into 2. And finally, this leaves 2 invariant, and that maps 2 into 1. So therefore, this is 1, 3, 2. Okay. So these are in class C2. These are in whatever. So we know that U2 of 1, 2 multiplied with U2 of 1, 3 is equal to U2 of 1, 3, 2, because this is a representation. Okay. So, I mean, yeah, whatever. So, but these are numbers which are also equal to the characters. So they are actually the same thing as the characters in here, because, well, that's a one-dimensional representation, because the character is actually the trace. And since this is a 1 by 1 matrix, the trace is equal to the that entry in there. So that's also a character in here. Okay. Yeah, whatever. I mean, let's not repeat the argument. So basically, the product of x and x should give you y. So therefore, x squared should be equal to y. This then implies that y is equal to 1. We don't have any other solution here. Okay, let's go back to this table and then mark y to be equal to 1. So that's the first thing that we are going to say. Okay, so in any case, so the next thing that we have is now we have like 2 options. So x is either +1, so either x +1 or x is equal to -1. Okay, but if x is equal to +1, we have already have the solution actually. I mean, if x is plus 1, basically in that case, this row is identical with the first row. We get the trivial representation. So, I mean, this x is equal to plus 1 already appears in there. So therefore, that's not our solution. So our solution should be that the x is equal to minus 1. Okay, so let me copy this so that I don't go back and forth. Okay. So then we get u1, sorry, we get u1, the trivial representation. If x is equal to minus 1, then we get basically the second one-dimensional representation. Okay. So therefore, I'm going to do this copying in here. So therefore, we have found these two numbers. So that's equal to minus 1 and that's equal to plus 1. So we can also check the orthogonality in here. I could have found this number by using the orthogonality as well. So that's also going to give me the same number. Okay, so here, let's just note that, for example, what's the meaning of U2, right? On the group S3, U2 is basically the signature function. I think I have shown this as the epsilon thing. So epsilon G, I have defined this as plus 1 if G is an even permutation, and minus 1 if G is an odd permutation. Okay, so all the transpositions are odd. All the transpositions are odd, so that this is the transposition. This is the class of transpositions, basically. So the signature gives you minus 1. All the 3 cycles and the identity, they are even, so therefore their signature is equal to plus 1. So that's the meaning of that. So basically, U2 is the same thing as this signature function. Okay. It turns out that, well, let's say it like this. In general, let's say in the symmetric group Sn, there are only two one-dimensional irreducible representations, right? Well, basically, U1 is the trivial one, and U2 is the signature. Okay. Physically, there's some kind of a physics applications for it. So for identical particles, for example, the exchange of the particles is a symmetry. So the symmetric group is basically the permutation group in there. And we would like to find how wave functions change under these symmetry operations. So the one-dimensional representations are basically correspond to situations where under a permutation symmetry of this of these particles, the wave function doesn't change. At most, it gains an overall phase, which actually doesn't change the physical state. Okay? In any case, it turns out that this trivial representation corresponds to the boson. So the boson wave functions actually transform under permutations like the trivial representation. Fermion wave functions transform like the signature representation under permutations. Okay? So we don't have higher dimensional representations in here, but in applications, these other representations are also used. Okay, so this is just an extra information in here. So these are kind of like useful representations actually. There is also a two-dimensional representation. So we would like to find these Z and T. There are a few things that I can say in this case, all right? But let's just remember that these one-dimensional representations, these are both representation matrices. I mean, these characters can be considered as representation matrices themselves, as well as the characters, right? However, for two-dimensional and bigger representations, these are the characters. Okay, so for example, for identity, the corresponding matrix is the 2 by 2 identity matrix, right? As a result, the matrix is going to be different. And I mean, depending on your taste, you may actually, by a similarity transformation, you can change the matrix to something else. Okay, so this Z in here and T in here, they are characters. So they are traces of these matrices. So I'm going to write this thing down. So for example, in that case, Z is equal to the trace of U3 of G for any G within the second class, for any transposition basically. So the matrices can be different, but the trace is going to be the same. Okay. So for one-dimensional representations, we have said that, well, in that case, the character is a root of unity. Can we say a similar thing here? And the answer is more or less yes, right? So the idea in here is this. This is a 2 by 2 matrix, right? U3 is a 2 by 2 matrix. Okay. U3 of G, for example, right? In that case, the trace of U3G is equal to the sum of the eigenvalues. I mean, eigenvalues of that matrix. Eigenvalues. You can consider them like that. Okay. You can also consider it like this. So if you know the eigenvalues, you can make a similarity transformation and then make this actually transform this to a diagonal matrix where the diagonal entries are the eigenvalues, for example. And you can also think of it like that. Okay? So the idea in here is this. Okay. So suppose, I mean, G, for example, is an element with order 2. So that means U3 of G squared is equal to identity. It's a 2 by 2 identity matrix. So that means the square of that matrix is equal to identity, right? I mean, the relationship satisfied by the abstract elements of the group is also satisfied by this representation matrices. So if a matrix, the square of a matrix is equal to identity, then the square of the eigenvalues should also be equal to identity. So lambda 1 squared should be equal to 1, and lambda 2 squared should be equal to 1. Why? Because, I mean, if this is diagonal, in that case, the diagonal entries will be the eigenvalues, and taking the square of the matrix would actually be obtained by squaring the eigenvalues. And if that's equal to the identity matrix, that's basically equivalent to all the eigenvalues being equal to 1. Okay. I mean, there are actually more formal ways of doing this. But in any case, so the idea in here is this: if G is an element with order M, and A is any representation, then all eigenvalues of AG are nth roots of unity. Okay, so in that case, if we have a bigger matrix, not a 1 by 1 matrix, but a bigger matrix, in that case, we say that the eigenvalues are the roots of unity. If the representation is one-dimensional, then this is a number, and that number is a root of unity, nth root of unity. So let me write this in an unambiguous way. So that's the M, right? Okay. So that means, in this case, for example, this Z, for example, is basically equal to All right, so I'm going to write it in here with that color. So Z therefore is equal to lambda 1 plus lambda 2, the sum of two eigenvalues, where each lambda I is equal to plus minus 1, which means that Z is equal to either minus 2 or 0 or plus 2. Okay, I can do the same thing for T, right? For the last one, right? It's that element in here corresponding to the conjugacy class of the 3 cycles. So T is equal to, let's say, primes in here, lambda 2 prime, where lambda I prime is equal to either 1 or e to the 2 pi I over 3 or e to the minus 2 pi I over 3. Okay, I'm going to show that this basically the sum of these two. I mean, the eigenvalues are this one and that one, and their sum is equal to minus 1. So therefore, T is equal to minus 1. And Z is actually equal to 0. So because, yeah, whatever, the opposite eigenvalues actually appear. Okay. In any case, that's one thing that we can actually say about these two elements. However, what I'm going to do is, well, I'm just going to apply this orthogonality of the columns. Okay. So orthogonality of the columns says this. I have written down the relation above that chi mu k complex conjugate chi mu L, that's equal to delta KL, the order of the group divided by the number of elements in the conjugacy class. Okay. So this says that when K is different than L, the right-hand side is equal to 0. So therefore, that factor does not have any importance at all. This says that the two columns in here are perpendicular to each other. They are orthogonal. Sorry, let me write minus 1 in here. So I'm just going to do this for the first two columns, for example, and this and that column. Okay. So I'm going to write down the relationship like this. So 1 times 1. So that's basically for K is equal to 1, L is equal to 2. So therefore, 1 times 1, 1 times minus 1, 2 times Z. 1 times minus 1 plus 2 times Z is equal to 0. But this is already 0. But this implies that Z is equal to 0. And for the element T, I need to look at the orthogonality of this column with that column. So the elements are 1 times 1 plus 1 times 1 plus 2 times T is equal to 0. So that part is equal to 2. So therefore, T is equal to minus 1. Okay. And then that finishes the character table. So this is the full character table of the group S3 or E3. Okay. So we have been able to identify the character, but we couldn't. We haven't found the representation matrices. This is a different story, right? To find the matrices themselves, we have to do something else. But this is the part that we actually do a lot. And so as a result, sometimes finding the character table and sometimes, reading the character table is an important feature. It's an ability that we always have to gain. So the last thing in here is this relationship. So this is basically for group S3, but I would like to say something more general about these representations. For now, this is going to be enough. Let's say that we have a group G. Group G is, this is a theorem, is abelian if and only if all irreps all irreducible representations of that group are one-dimensional. Okay. I have like just only 2 minutes or something like that. I would like to show it actually in that short time. But basically, if a group is abelian, then for abelian groups, we have only one-dimensional representations. And it turns out that there's also a converse. So if a group has only one-dimensional representations, then it must be abelian. The connection is this. So first of all, for abelian groups, to show, for example, this implication, so I'm going to assume that G is an abelian group. So if that's the case, we can actually look at the conjugacy relation actually. So in the conjugacy relation, we have actually a similarity transformation, if you remember. But if the group is abelian, then all the elements commute. And so therefore, the similarity transformation does not change the element. So therefore, every element is conjugate to itself. Every element is conjugate to itself, right? Let me write this thing down. Two elements are conjugate if and only if they are equal, okay? This therefore implies that all conjugacy classes have one element, okay? So each of these conjugacy classes have only one element, which means that the number of conjugacy classes but that C is equal to the order of the group. But we also know that this is equal to the number of irreps. Okay. So finally, we use this dimension relationship. So sum of the squares of the dimensions is equal to the order of the group. But here the number of the irreducible representation is equal to the order of the group. So there are like G terms in here, right? So we have G numbers in here. Each one is a positive integer, and their sums and squares should be equal to the order of the group. So the only solution is the solution where all of these dimensions are equal to 1. Okay, so that's the end of the proof. And the nice thing is I can go back, right? If all dimensions are equal to 1, then therefore the number of terms in here should be equal to the order of the group. So that's basically the number of irreducible representations, which is equal to the number of conjugacy classes, must be equal to the order of the group. So all conjugacy classes have one element. Yeah, whatever. Then we reach to the conclusion that the group is an abelian group. All right, let me finish it in here. But we are going to say something more about the character tables of the abelian groups later. Next week, I'm going to start with some physical examples, actually.